All right, this video is the second of two videos in a series. The first video talked about how to find the component form of a vector, such as the vectors written up top here. Again, notice v vector, it's got that vector on top of it there, is -2, 5. So down on our screen down below here, you'll notice it's drawn out. -2, 5 is this blue vector here, right? That's vector v. Now, a vector, again, can start in any position. So notice I don't have an axis drawn, but if you counted from the beginning to the end of that blue vector, right, we went left 2 and up 5. So again, basically, that's vector v. The same thing goes for vector w. It's in red down here, right? This is vector w. Notice it's 3 units to the right and 4 units up. If we counted horizontally and vertically, right? 3 right, 4 up, which is exactly, again, what we have up top here, right? Those angled, sort of squared off brackets, 3, 4 though. 3 to the right, 4 up. Now, really what we're talking about in this video, though, is what's called the resultant of a vector. The resultant of a vector is basically saying we're going to add two vectors together. And realize that we sometimes represent that. We can say that, a product of a vector and a scalar, right? 2 times a vector can also be called a resultant. Mostly because, again, 2 times v is really just like saying v plus v, right? It's like adding a vector to itself. So just realize that, again, resultant is a little bit of a wide term, right? It can be a little bit more sort of widely used. Oops, and I got rid of my symbol there. But technically, if somebody just says find the resultant, what they're saying is add 2 vectors together. Now, in order to do that, what we could do is say we're taking both those vectors and we're going to sort of travel along both of them. So like, let's say we were traveling vector v, so we traveled that blue line, then we traveled vector w. From the end of vector v, we're going to place vector w, and notice we end up way up here at the top, right here. So we started down at the bottom here, and we ended up right up top there. Well, technically, draw that a little thicker there. Technically, we can add in either order. So if you wanted to, you could have traveled w and then v. But notice you'll still end up in the exact same place. Okay? And in fact, if we look at it, we could take the component forms of the vectors. Again, vector v being -2, 5, plus vector w, 3, 4. And we could add the horizontals, -2 plus 3, and 5 plus 4, and you would have ended up with a vector of 1, 9. Oops, that's a bad bracket there. 1, 9. Well, if you count out that orange vector, doesn't it look like from the beginning we traveled 1 unit to the right, and then we traveled up 9 units to get to the end of that vector? Again, a vector is more about magnitude and direction. It's not about where you started and ended. It's how did you get from point A to point B, right? From the beginning to the end. Well, we traveled 1 unit horizontally and 9 units upwards. And that's our path or our direction, our magnitude and direction represented on the screen. Let's do the same thing with 2v. Again, we could say 2 times the component form, -2, 5. So algebraically, we can find this, right? Well, basically, what we're going to do is distribute our 2. 2 times -2 is -4. 2 times 5 is 10. And if we actually took our vector v, right, we transferred it over here. I'm just going to start it way down at the bottom here. And then we took another vector v, right, 2 of them. Doesn't it look like we basically went left 4 units, -4, and up 10 units, right there. So again, vector 2v, right, or twice v, multiplying it by what we call a scalar number, right, just a simple, numeral, simple number. We multiply by a scalar, we basically doubled the vector. We've doubled its length, we doubled its magnitude, right? And we could actually find the magnitude of vector v if we wanted to, using our, I think that'd be a good little experiment to do. Let's go ahead and do that real quick. The magnitude of v would be -2 squared plus 5 squared, and then we take the square root. Well, 4 plus 5 squared will be 29. So that's the square root of 29. Well, the magnitude of 2v, right, is equal to the square root of negative 4 squared plus 10 squared, or basically the square root of 16 plus 100, the square root of 116, which if you divide by 29, you would actually get 4. So this actually comes out to the square root of 4 times the square root of 29, or basically 2 root 29. We've taken our magnitude and we've doubled it, right, by doubling the vector. This is what's called the tip to tail method. You just start at the tip, or the tail of one, you draw that vector, and then that becomes the tip of one vector becomes the tail of the next vector. We sort of do them almost like you're walking a path. Let's take a look at doing that a couple more times. If I want to find v plus 2w, again, v was the blue vector, I'm going to walk that blue line, right? So I'm going to go down here and I'm going to walk right along that blue line, but then I want to walk 2 w's. So from the end of vector v, I'm going to place vector w, and then I'm going to place the vector w again. Now you can walk those in either order, so technically we could have gone 2w right away, because we're just adding, right, commutative property, and go in whatever order we want. Then vector v. Technically you could even go w, then v, then w, and you'd sort of kind of cut through the middle here, right? You'd go red and then blue and then red. But in the end, all that really matters is we've gone from start to finish along that diagonal, right? Which, in that case, would have been negative 2 from v plus 2 times the 3 from the w, right? 2 times that horizontal component, comma, again, 5 from v plus 2 times the 4 from w. And basically it becomes negative 2 plus 6 is 4, and 5 plus 8 would be 13. And if you notice, we went 4 units to the right, and we essentially went up, right, 13 units. And it makes sense that's where we ended up, in that case. All right, let's do one more very quickly, and then we'll call it a day on this video. Make sure, again, you watch the third video in the series. It's called Unit Vectors. It's going to talk a little bit more about this sort of stretching of a vector or shrinking of a vector and what we can sort of talk about using those. One last sort of note to make here, though. What if we wanted to subtract vectors? Again, the resultant of a vector is adding 2 vectors together, or sort of multiples of vectors. What if we subtract? Well, essentially, it's like saying negative v. So we want to go backwards v. So if we took that blue line, well, we walked w, right, w minus v. I'm going to take that blue line, but instead of traveling upwards, right, instead of taking this blue line and going up, I'm actually going to go from the tip of the red one backwards. So if I could flip that blue one around, right, I can kind of do that. What if we went this way? Well, our resultant vector would be traveling from the beginning to the end over here, right? And again, we could form that full parallelogram if we want to, but what you really want to notice is, again, looks like we went down 1 unit, and we went to the right 5 units. Again, the same thing as saying w minus v, right? And again, minus the negative becomes plus. And in that same case, w, the vertical component, minus v's vertical component. And 3 plus 2, there's where we went off here. 3 plus 2 would be 5. Remember, we went 5 units to the right. And 4 minus 5 would be negative 1. And remember, we went 1 unit down. Again, you can also subtract vectors. Algebraically, it makes sense. And in the picture, you just have to remember a negative vector is just a vector in the opposite direction. I hope that helps you, again, drawing vectors. If you have any questions, talk to your teacher. And otherwise, have a great day.